Thanks a lot, Shen-Yuan, and thanks a lot for joining me to this discussion. And I will try my best to explain our latest discovery from Hong Kong. But if you feel any part is not clear, please stop me, and I will try to make clear for you. Because this is most likely my problem, not yours. Right? In my department, I'm famous with constantly got the lowest teaching grade from students. Right? So it's most likely my problem if you find something not clear. Okay, as Shen-Yuan just mentioned, my team started with doing observation, but then very soon we find that we cannot find a good simulation from literature can interpret our result. So the best way we think is, why don't we also try to do simulation ourselves? So we started 10 years ago, so we start to be able to do some simple one recently. And as Shen-Yuan also introduced, my thesis actually majority is in instrumentation, and very luckily in Hong Kong they have this kind of funding. So actually we collaborated with ASIAA trying to put the camera/polarimeter to the GLT. Okay, so this is what we are trying to do. But today we focus more on the observation simulation part. Okay. And all this effort is for one single purpose, is star formation, of course. So I'll give the background of star formation, the current status, my biased point of view, and why we want to study turbulence, magnetic field, so an overview of a cloud, and our comparison between these different methodology. Here it's easier to convince people star formation is interesting, but in Hong Kong, the whole Hong Kong, we probably have 15 astronomers of the entire Hong Kong, with all universities add together. So in that environment, it's hard to convince many people why star formation is an interesting topic. Because most people, they think, how difficult could it be? It's just a concentration of mass due to gravity. Right? This point of view is not wrong, right? Because many structures in the universe is actually formed in this way. It's an amazing illustration, simulation from illustrates here. They actually start the primordial density fluctuation inferred from CMBR. They're inflated by dark matter, and let everything evolve under gravity. Then 13 billion years later, they can find this cosmic web structure in their simulation. And not only so, they can even zoom in all the way onto individual galaxies. This is not a photo, it's from their simulation. So it's all under gravity. But however, from here to stars, the last miles, since it's not that simple, right? As in no group can really propagate to here through galaxy. And not only so, even the cradle of star, the disks, right, still, as in no group can claim they can create a realistic protostellar disk, right? For realistic, I mean compared to observation, right? From any kind of initial condition they tried, not to mention from galaxies, from cloud or core to disk. No one can do this. And not to mention, many people treat this as the holy grail of star formation theories, is to explain the initial mass functions. I don't think here I need to explain too much about this, right? But these are all today, I won't be able to even getting close to answer these questions, right? But as I will show, we got stuck on this process here for a long time, right? The molecular cloud, right? So we're still far away from individual stars because we start here. Lots of problems we still encounter in this stage, and some problems probably more than many of you expected. Some are considered probably resolved, but I will show you today that no, it's probably not. Okay, so cloud, suppose, has the answer. So here, a quick history of the theory of clouds to star. Gravity, Jeans mass, magnetic field in the 50s, turbulence in the 80s. Okay. And nowadays, I think I used to think that most people should consider both turbulence and magnetic field in their models, right, in order to shooting for these goals, even though we are far, far away, but it should be, at least should be considered. So this is the slide I would share before the COVID pandemic. I was thinking, so this has to be the picture. And we astronomers be working hand in hand toward the goal of star formation with the understanding that you cannot ignore turbulence and the magnetic field and B field and gravity. But after the pandemic, I've been to 2 major international conferences. One is in Lyon last summer. I surprisingly found that I'm also one of the very, very few astronomers there try to analyze the effect from magnetic field. Majority in that conference, people still consider turbulence is the most important one, dominant one. And I made very famous, well-established theorists talking about why you think you can ignore data like from Planck. Right? The answer is still the same as 20 years ago when I asked the same question. They consider polarimetry cannot look deep into cloud. They look at the surface. Of course, it's not true, right? As many of you work on observation polarimetry, you probably know why it's not true. But unfortunately, people can still have the same mindset. Right? When observation disagree with theory, some people assume observation is wrong. But what even surprised me more is that this past May, I was in a conference in Germany, Apples. I was surprisingly found that they don't invite the people working on turbulence. Okay? Because my problematic personality, I become the only one there defends turbulence. This I feel really strange. This never did this first in my life. That's the first time. In that environment, people consider the line width people usually observed can come from outflows or gravitational contraction. They don't think turbulence is necessary, but which is also not true. Right? I will get into this later today. But my point of view is the same. I try to maybe illustrate more to you that the whole process I call is the Tai Chi of gravity, magnetic field, and turbulence. All of them play a role in this process of concentrating gas to stars. It's a very quick point of view. In this picture here from Taurus, we can see all these kinds of forces. Right? The color here is not density, but stands for different velocity. You see, if you have a smaller scale, you got closer colors, means similar velocity. But if a larger scale, you start to mix different colors, means you have a more different velocity. Right? And this is a property of a turbulence. It's a very crude way to describe it, but it's possible. I cannot do it today. I actually tried to do this in Shida last week. Is from this set of data, the PPV, you can derive the turbulence Kolmogorov type spectrum. That spectrum is the evidence of turbulence. It has been done. Right? So turbulence is another problem. It's observed. And because of this turbulence, you can imagine it like a wind. Right? So the whole mass here is not able to collapse free fall. Right? These winds will prevent them from collapsing free fall. So turbulence, to some extent, support the cloud. At the same time, the turbulence are supersonic. Right? So the whole volume is compressible. So for smaller scale, they can enhance the density and help concentration of the mass. So turbulence play 2 types of roles. So this the effect of turbulence to gravity, but gravity can also feedback to turbulence, and it's hard to observe directly, but I will show you some indirect evidence for this direction. You probably can also notice, not very clear here, is that it's those fine white lines going through the structure that actually magnetic field orientation. And you probably can see that the structure elongation of the cloud is roughly perpendicular to the B field. Right? It's most likely due to the strong B field make the gravitational contraction anisotropic. Right? So the mass is easier to contract along the B field because perpendicular direction there's a Lorentz force. Right? If the contraction is anisotropic, and this is what you expected. Right? an elongated cloud perpendicular to the B field. So the B field control gravity is being seen. And also, one of the important topics we're going to talk about today is the B field density relation. And many people use this relation to argue that gravity is indeed the compressed magnetic field. And the action between turbulence and magnetic fields also observed here. If you observe the turbulence spectrum, which I just mentioned, it can have anisotropic properties, which along the B field direction, the turbulence is more coherent. In other words, it's less turbulent. But perpendicular to the B field direction is more turbulent. Okay. These are all observed and also theoretically expected. Okay. So because of this, I think you cannot drop any force here in order to understand star formation. This is my point of view. But what about others' point of view? And here's a quick history from some monumental papers to try to tackle the same problem. From almost as old as me, already people study about the B-N relation to understand how B field can affect gravitational contraction. And in the 80s, turbulence is discovered. And in the Frank Shu kind of review, they prefer to focus on B field because turbulence is considered will dissipate very quick at small scale, right, which is also theoretically expected. But 20 years later, the same journal review series, the spotlight falls on turbulence. In this review, almost everything created by turbulence. Okay. And only like 40 years, right, after these kind of theories proposed, finally, after the lifelong effort of Dick Crutchers, we think we have the data to put constraint on the theory here. So here, see why they want to observe B-N relation is to put constraint on the theory here. Okay. At the same time, I try to be humble, so I don't put myself to the monumental papers, but I did something here, is I show that the B field is actually quite ordered from the intercloud median to the cloud core, right? So if it is ordered, somehow this again, so the turbulence is that dominant. Otherwise, B field cannot be that ordered. Okay, it's a very quick review of what happened before the first decade of the century. So this will be the background of the discussion, the following discussion. So first, just a little bit of a theory and why this kind of plot can be able to tell us how important B field is on regulating gravitational contraction. This is the induction equation, shows that B fields will vary due to two reasons. One is coupled between the gas, velocity of the gas here, and also it can diffuse by itself. But for the majority of molecular cloud, we can talk about what's the majority after this talk, which is not the focus of this talk. But majority of the cloud, you can ignore this part, which is a good approximation to drop this, and everything will go to flux freezing, which assume all the B field will couple with gas. Under this condition, if you have a very strong magnetic field, then contraction can only happen along the field, right? As we discussed before. So B field can stay almost constant when density enhances. In the opposite scenario is if B field can do nothing to affect gravitational contraction, and you should get B field proportional to the 2/3 power of density. It's very simple to understand because this direction of the compression along the B field cannot enhance the B field, but it can enhance density. Right? So B field will enhance a bit slower. Okay. So this why proposed here that you find this slope here, you can judge whether B field is important if it's much slower than 2/3, almost doing nothing to regulate contraction, which we got 2/3. Okay, this is the very quick background. But in reality, it's not that simple. If you do this, you put this into computers, simplest possible simulation. You got the fixed amount of mass of the sphere, but you control the B field trends such that you can get just critical condition or highly critical condition. And you will find that when the criticality is just critical, means that B field is just enough to support the gravitational contraction, okay? Or just a little bit smaller, so contraction can indeed happen. You won't have a constant slope. You will have this kind of a B-row relation. So it's not a constant slope. Okay? It starts with a 2/3, but it will get flattened, so transfer to this condition. Well, it's not hard to imagine why. Right? If you play guitar, you try to compress your string. At the beginning, you can compress the string, but to some extent, your force is not enough to keep on compress it. Right? So same thing happened here. If the force is enough to compress the B field at the beginning, it's got 2/3, but then the magnetic tension build up, and magnetic pressure also build up, and so the compression will be getting less and less easier, so it got flattened out. If the gravity want to always keep this isotropic contraction, to keep the 2/3 power, it have to be at least order of magnitude higher than the critical value. So when you see the 2/3, if 2/3 indeed happen, it means the gravity or mass is 10 times, at least 10 times the critical needed mass to achieve so, to keep the 2/3. It's very intuitive, but theoretically it's difficult to derive because the critical value is a function of the geometry of everything, right? You see the complexity here. But through simulation, you can very easily to see it's roughly at least order of magnitude is needed. Okay, so theory, point of view, simulation add some more detail to this. How about observation? Observation needs more power. Yeah. So, okay, I got my laser only left. Good. Observation, voila. Observation got 2/3, so problem solved. 2/3, 2/3. What do we ask for? But on the other hand, it's only one tracer. Another tracer is sub-millimeter polarization. Many of you are probably familiar with this, but we will skip the principle today. But you just believe this is B field inferred from polarization. And if you want to make connections, you probably make, okay, here, 2/3 connected 2/3, and these very ordered, elongate in this direction, more related to this one. Okay. But if you make this kind of connection, you will bump into trouble. Because here, criticality less than 1, but here, criticality larger than 10. How can it be possible? It's impossible. So it has been recorded as one of the mystery in the recent PPVII review. But you think carefully here. Here you got the B-N relation. Here you got the figure, right? You got a picture. How can you compare just like this? You have to make something similar comparison. You have to see the structures, probably versus density, or easiest versus scale. You should compare something like this. So here's the B field structure inferred from polarimetry versus scale. Here, smaller scale means higher density, right? It's the nature of observation. So immediately you see something similar, or at least you don't have to assume where you contains 2/3 power. The B field have to be ordered. No, it shows that if you go to high density, small scale, observation shows B field doesn't have to be ordered. So in some sense, this problem is solved. It's not a problem at all. But there's more serious problem, which I pointed out 10 years ago already, but only I consider now I resolved this. Is this a problem? You take the same data, Zeeman measurement, instead of plot the B volume density, you plot the B column density. And you will see a different picture. Why B column density? Because we talk about the critical mass flux ratio. It can be translated here. It's given the B field. You will find the critical column density that's allowed to collapse. It's purely theoretical. You can calculate this critical density, column density of a given B field and plot it. It will show as the dotted line here. And you might consider, okay, if you really want to collapse, the cloud want to collapse, it have to overcome not only B field, but also turbulence. So we can roughly assume equipartition. So turbulence is as energetic as the B field. So the total energy will become doubled. So you got this dashed line here. So the reality probably happens something between these two lines, but we don't have to be that precise because we already see something interesting here. So then given the observed B field strength, which is around here, 8 to 10 microgauss, this observed B field strength. For some of you, if you don't know Zeeman, you might say, how about this dot here? So the property of a Zeeman measurement is that you can only see the B field strength of the line of sight component. So due to projections, you won't be able to see the total B field strength. If you want to see the total B field strength, you have to do complicated Bayesian analysis, or can be 80% as good, is you just look at the upper envelope. Because upper envelope happen when you have a good luck with the line of sight parallel with the B field. Right? So upper envelope can show a total B field strength and density correlation. So that's why we can use this upper envelope, 10 microgauss, to estimate total B field. And given this total B field, theoretically you expect a turning point about 5 times 10 to the 21 column density. It seems the data seems to happen right here. It's turned. And after it's turned, it stays with this critical value here. But note here, this line here are different Bayesian analysis to fit the data, upper envelope. Here is no fitting. The blue belt is theory, and the data fit the theory very well. So if the cores are 10 times above criticality, all the data should drop below this line here. But they're all very close to just critical. Okay, it's not a fit, it's a theory. So here is a discrepancy immediately here. If you want to interpret all the 2/3 to say that it's 10 times critical, but which is against another picture here from the same set of data. Okay, I spent 15 minutes for introduction. Okay, good. I think we're fine. Okay, how about some other observations? It's not so critical for today's discussion, but since I mentioned observation, why don't I just advertise something else, right? It's just very quickly. We also observe the cloud tend to be parallel or perpendicular to the B field, which also not too surprised, right? If you have a strong B field and contractions and turbulence both are anisotropy, your cloud shape will be related, right? This cloud shape will not be circular. And both turbulence and contraction, they are anisotropic. You can imagine if you observe the velocity also be isotropic. Yes, the velocity anisotropic also observed. So the cloud is against torus. The cloud is right here. So in the diffuse region, blue means the turbulence eddies is aligned with the B field, which is theoretically expected, turbulence and anisotropy. And the red region is the opposite. It tells us that the velocity dispersion is largest aligned with the B field, smallest perpendicular to the B field. Here, blue means velocity is more coherent along the B field. It's very easy to expect. This year is another peak of the 11-year solar wind cycle. Right? So if you want to see aurora, go this year. And the aurora happened because the Earth's B field channel the solar wind to the polar region. And now replace solar wind by turbulence. Turbulence will also be channeled by B field if B field is dynamically important. That's why we got the blue color here. Along the B field, velocity is more coherent. But the red, the velocity is not turbulence, it's gravity. So they collapse. Okay? The B field in this direction collapse, meet along the B field, meet here. So along the B field, the dispersion is largest, and perpendicular is smallest, is more coherent. So this velocity anisotropy is also observed. Another name of it, much more famous name, is called VGT, velocity gradient technology. Right? It's the same thing, but we discovered it first. We don't use it as a tool, but when people use it as a tool to probe a B field, right, you can think the oppositely. If they have correlated B field and velocity anisotropy, you can use a velocity anisotropy to probe B field. Right? It's a different story. And also its alignment can affect fragmentation. This is the mass accumulation function. They have different distribution from different alignment. And these actually infer to different star formation efficiency. I will stop talking more about this, right? But this is main observation, and this one is what we're going to use today. Okay, if you are as old as me, you probably know this guy. If you don't know this guy, you probably know the big bird from Sesame Street, right? And this what monster I forget. When I see this, I feel about my career. In order to be an astronomer, you need to understand theory and observation at the same time, because only by close comparison between these two, it's possible to make any progress in your understanding of the phenomenon. Right? However, star formation is so complicated. If you only do these two and compare by your eyes or simple numbers, you probably will make a mistake. For example, you probably will conclude that magnetic criticality has to be 10, much larger than 1 if you see this, and you interpret it with this kind of theory. Right? Because star formation, cloud is so complicated, it's magnetized turbulence with self-gravitating, and beyond that, when you do observation, you only observe the projection of the B field on the sky and projection of the turbulence along the line of sight. Just so complicated, right? It's impossible to put things together and remotely connect to theory. The only possible way, I feel, is you really have to depend on simulation to combine these two together. Right? And here is more detail how to do this. And for theory, emission equations, some of the equation are showing here. Right? This one is nothing but F equal to ma. The left-hand side is changing the momentum, right-hand side all the forces. So understand the complicated systems here, how to do it. But the theory gives us a direction. Also give us a direction of what to observe. For example, we might wonder the turbulence term is mainly, right, this theoretical part, turbulence term is mainly coming from its convection term. And if you want to know the relative trends of turbulence and thermal motions, you want to compare these two terms, right? Convection term to the thermal pressure term. And you do this comparison, you will find the unit of Mach number. The result is Mach number. It's why people want to observe Mach number. So cloud is observable. It's usually quite supersonic with very high Mach number. And you might also wonder, how about turbulence energy compared with magnetic field? So you compare these two terms, this divided by this term, which will actually give you ever Mach number. You might get different answer from others, but based on my observation, the ever Mach number for the cloud should be less than 1. So the cloud turbulence is slightly super-Alfvenic. What else you want to study? How about turbulence or convection velocity versus internal friction? If then compare these two terms, this will bring you so-called Reynolds number. If the Reynolds number is very big, means you can ignore the internal friction, and the result is always turbulence. So cloud, from the theoretical point of view, it also should be very turbulent. What else we can try? How about induction equation? We see this. If we compare these two terms, convection term to the diffusion term, if the number is very big, you can ignore the diffusion term and claim that flux freezing is a good approximation, like what we have done today. For a typical cloud, the entire cloud, you got 1,000 for this ratio. So it's not too bad to just drop this term, which helps the simulation a lot. And if you compare gravity to Lorentz force, you end up with the so-called mass to flux ratio. So critical mass flux ratio showing the critical condition for mass to collapse the B field, to compress B field to collapse. And this is the main point of today, right? Because we don't know it's just critical or 10 times supercritical. So this is open question. It's also guided from theory. Right? If we can answer this, we don't know this part of the theory. Okay. So the just some observation I showed already, right? That if we put those observed conditions, supersonic, super-Alfvenic, flux freezing, those properties into simulation, you should expect to see this from your simulation. If you don't see it from your simulation, then something is wrong, right? And your simulation have to replicate not just one, but should be both of them. If there's a third observation, your simulation should replicate the third observation. Otherwise, your theory is wrong. It's just a basic, should be a basic training of all scientists, right? But I think this is something is missing in current society is if you show an observation to people doing simulation and they cannot replicate it, usually the first reaction from them is, oh, your observation is wrong. Okay? But today, we don't want to do this. We assume all the observation to some degree catch the true characteristic, and your simulation should be able to catch those. Right? Otherwise, we consider simulation is wrong. Right? Let's try this different point of view, right? Which I seldom find. So we put those initial conditions and just perform very simple simulation. Oh, but before then, I want to ask you one more question, which is, I think, is very apparent, but has been ignored since the very beginning of this business. We compare these two. We say theoretically 2/3, criticality larger than 10. We observe a 2/3. Okay, this is good. We're done. But is this really so? Here, we have one core, and following the involvement along the time axis, we can have this relation. Right? But here, you got 100 core, and got the relation from the current snapshot of the sky. And this, I showed the simulation of this before to show you how it's possible to have the 2/3, and that simulation takes millions of years. So one core, a million year, 100 core, a snapshot. Then how can you compare the two? It just doesn't make sense at all. Right? But you can assume maybe for some reason, this I call it spatial relation, can infer temporal relation. But this is logic jump. You need proof or disproof. So another important thing I want to raise today. Okay, then I got 20 minutes. Yeah? Simulation, all observed. Supersonic, super-Alfvenic, and criticality. Wait. This is what we are going to find out. Why you put the criticality in your initial condition. Okay, here is, at least I think, people is more for the cloud, not the core, right? Overall molecular cloud. It's less of an argument that the cloud as a whole is around the transcritical. Otherwise, the whole cloud will collapse, right? You have a lot of star formation. So if the whole cloud is not that efficiently all converted to stars, at least it should be transcritical. So this criticality is the entire cloud, not the core. Okay. So everything from observation and this logical argument, the whole cloud is just slightly critical. We got the cores. We got core 1 evolved along the time, core 2 along with time, core 3, I showed the movie, evolved along with time. So now we are in hand to have this temporal relation. And here it shows a snapshot of the simulation. For this snapshot, we can get the spatial relation to mimic observation. So we got everything here. So what's the result look like? So now the red and blue are 2 snapshots. Million years separated, million years apart. So it's quite encouraging to me is I see the 2/3. Okay. So snapshot, mimic observation, I got 2/3 in high density, which I didn't show here, but you can see the trend. If you go to lower density, it's become flattened, also similar to observation. Right? This is encouraging. And moment of truth is how about temporal relation, which compared to this classical theory, in showing in the dark line here. So for this guy, this is the core 3, this is zero relation, no 2/3. And this core, even going backwards, is slightly expand. And this core is contraction and rebound. So if you have the picture of a turbulence, okay, you'll probably more be able to imagine why the temporal bill relation should be more like this instead of a constant value. See, turbulence is playing a role here. Okay, and I forgot to mention one thing is in this plot, this value is overall initial condition, but when the core forms, you dig into each core become super-Alfvenic. 0.6 overall, what do we put in? But it got enhanced inside core. Super-Alfvenic turbulence. And criticality of each core is also agree with the observation from the B column density relation. They're just critical. They are not 10 times critical. Just critical, slightly super-Alfvenic. So this just critical cores, of course, will not give you this 2/3 in temporal relation. And we don't see this in temporal relation. So this is not 2/3, this is not 2/3, and this is backwards, not 2/3. But in the spatial relation, in the snapshot, you really see the 2/3. So then what is the reason of this snapshot in this special 2/3 relation? Need a completely different explanation than this. It's a different thing. Okay. And in particular, this red snapshot, right, on purposely we take snapshot before we even turn on gravity. So in the red snapshot, there's no gravity, and still you got a 2/3. So this 2/3 needs other interpretation. And before we spend our energy on this, maybe the whole thing is wrong if the model cannot explain this observation. Right? If it cannot, I will abandon these initial conditions. Maybe something wrong. So let's have a look. So this is what we have of a B-field morphology from larger scale to small scale, low density to high density. We see very similar thing. Is larger scale, low density, it preserves initial condition. But you go to high and higher density, you got more and more B-field structures, just like observation. This, okay, means this simulation is probably fine, right? It's not being discriminated yet by this observation. So next, what caused this and this? actually we mentioned the answer already, because for the high density cores, it's become super-Alfvenic. Super-Alfvenic turbulence can randomly compress the B field in random orientation. Okay? So when the compressed B field is perpendicular to the B field, it will enhance the B field. When the compression is along the B field, it will not enhance the B field. And when it happens in random orientation, statistically, will be just the same as isotropic contraction. Random contraction, isotropic contraction, statistically result the same, which is 2/3. And also because it is super-Alfvenic turbulence, of course, you will expect B field deviation significantly happen in high density. Okay, so this is actually we predicted in 2019 already, but by then we don't have observational evidence of this. And well, we do many different things in Hong Kong, so I haven't found a student to do this, but I'm happy to see in the PPVII review, it shows this result already. Okay, so every Mach number increases with density. Okay, we see this in simulation too. Okay. This, where you have strong turbulence in high density region, you know you can abandon this simple model already. And in your theory, you have to contain this term here to take care of the turbulence part. Okay, so it's a very different interpretation from this classical theory predicted. So the last thing, I think the time is okay. So the last thing is maybe we want to have a closer look to why this MA coming from. We put in, at a larger scale, sub-Alfvenic turbulence in order to preserve the largely ordered B field. But how come it becomes super-Alfvenic at high density? So here I have a simulation with the same amount of turbulence driving, but no gravity. Okay, and here is the so-called waterfall plot. Each line here means one snapshot of the time. And each snapshot, we look at the turbulence energy at different density. Okay, so we drive the turbulence until it's saturated, and at this point, we turn off the driving and see how turbulence can decay. Usually people expect it would decay in the turnover time. So here we see something like this, so energy will decay. Since you are not driving, turbulence energy decay. And the decay velocity is very similar over all density. It's not surprised at all. You can find this kind of, not this kind of illustration, but same kind of idea in the simulation from early this century. But what people didn't observe is when you have a gravity, and will this picture change? And what we show here is indeed it changed significantly. So in the diffuse regions, you have decayed velocity comparable, like there's no gravity. But in the high density region, you will see the decaying got significantly slowed down. So even you stop driving, this potential energy from gravity is able to maintain the turbulence only in high density. So we translate to the theoretical language in the literature, even like this, right? This will be the so-called energy decay rate. Usually people show the overall picture. If you do this, you will miss the high density because the majority of the cloud got the very low density. Right? So if you do the overall, or we just look at the low density part, or no gravity, you got this red line. More negative means higher decay rate. But if you have a gravity, and you still have this decay rate, but not a high density, because high density inherited the potential energy from the concentrated mass. I think I round out the time, and I didn't keep my promise. I have one thing to say, if it's allowed. Okay, so because people like to observe the right parameter. So this observation, usually if the parameter is below 2, people think, oh, the clouds will collapse. Okay. And this is our sample cloud here, sample core here. All our core have this value of a variety parameter. It's all well below 2. But only one collapse at the end. Right? This never collapse. This one is actually expand, and this one actually rebounds. Right? So the variable parameter, and here I don't have any observational bias. Everything is calculated from the simulation. So the variable parameter doesn't work as many people expected. You got something below, even below 1, it's not collapsing. The reason is not very remote, even though this plot might be complicated, but if I skip this plot, the thing that happen is, in the variable parameter, you only compare energy. If the gravitational energy dominant, you say, okay, it's going to collapse. But in reality, it's a force competing, it's not energy. When you have a strong B field, force is highly anisotropic. So it can be that you look at energy, gravity dominant, but you look at the force. They actually prevent the overall collapse of the core. So it's a bit complicated, but I'll skip the detail and try to end my talk with 3 slides of summary. So here, everything from simulation. We have a simulation set up by observed properties. Supersonic turbulence, subalfvenic turbulence, overall cloud just over critical, and you result in different kind of velocity anisotropy in the low density region, which is subalfvenic, and turbulence is highly anisotropic. And in these regions, B field is ordered, and in this region, you got BN relation follow this 0 index. And in this region, you got, again, ordered the B field. Okay? And this high density region where the velocity dominated by contraction instead of turbulence, you will have super-Alfvenic turbulence. The initial condition from low density region got enhanced due to potential energy. And because it's super-Alfvenic, it will twist the B field easily. So you will have this high velocity deviation from high density. And not only deviate, it compresses the B field. So you have this B-roll relation due to random compression. And all this should be checked by observation. And all observation actually exist. Velocity anisotropy, Mach number proportional to density, low density order the B field, low density B-roll relation have the index 0, low density order the B field. High density, super-Alfvenic turbulence, which should tangle the B field and give you large deviation of the B field, and also a BN relation of 2/3 power. So in case you lost, I have a cheat sheet here, which I follow Richardson and did this in Beidou, my hometown. So we just follow Richardson's point. Big worlds have little worlds. It describes turbulence, which feed on their velocity. And little worlds have less worlds, and so on to viscosity. But fields stretch worlds, channel their velocity. Except for neutrals at small scales, released by diffusivity. You might say, oh, where did this come from? I skip this, right? I have no time for this. But velocity in cores can be enhanced by potential energy, allowing worlds in turn to break field directionality and also compress the B field. Okay, I will stop here. Thanks a lot.